Okay, I guess we'll get started. Hi, everybody. Thanks for attending this webinar. My name is Jeremy Fink, and today what I'm going to be talking about are some tips and tricks for use when you're designing runoff reduction for a site. Let's see. Pardon me. Well, there we go. Okay, we got it. This is my contact information. If you have any questions after this presentation, feel free to drop me a line. I'm going to start off with a quick introduction about Hydro International for people who might not have worked with us in the past. And then I'll talk about some of the challenges that are involved in designing runoff reduction on a site for stormwater. And then a few tools that you may be able to use when you are designing your drainage. Some of these you might have run into in the past, some might be new to you, and then I'll go over some conclusions just to sum things up. Hydro International, it's truly a global company. We have an office on the East Coast of the US, in Portland, Maine. That's where I'm located. But also an office on the West Coast outside of Portland, Oregon. Company headquarters is in England. There's 2 offices there, and we maintain an office in Dubai to service a Middle Eastern market. And Hydro International does water treatment. We have a line of products for the stormwater market, a line of products for the wastewater market, and a line of products that's specially designed for the challenges of combined sewer overflows. The company is almost 40 years old. We have hundreds of patents worldwide and continue to do our own product development and develop our own IP for new products to meet clients' needs. The stormwater side of the business is about 30 years old, and we have thousands of installations around the country and around the world. One of the things that sort of makes Hydro stand out amongst their peers is we maintain our own hydraulics laboratory. We do all of our own product testing here, our own product development here, so we can really understand what makes a product work well, what needs to be improved, and we can do that all on our own schedule and meet our clients' needs that way. We're very proud of our collaborations with universities around the world. And these relationships are sort of a two-way street. Sometimes we're taking intellectual property that's been developed at a university and commercializing it ourselves, or we're taking products that have been developed at Hydro and giving them to universities for sort of a third-party independent testing. And then we work with regulatory and accreditation bodies around the world. And this is a similar sort of situation where we work with them to develop test protocols and work within their protocols to test our products. So that's kind of, you know, these are the relationships we have where it kind of gives you an idea of who Hydro is. And now I'll get right to the topic at hand, which is the challenges involved with runoff reduction. This is a diagram that I'm sure most of you have seen before in one way or another, how stormwater leaves a catchment pre-development. And just to kind of set the scene here, you know, in a pre-developed state, most of the water leaves a site through groundwater infiltration of one kind or another, whether it's interflow or base flow. A portion of it will be taken up into vegetation on site and leave through evapotranspiration. And a small percentage of it will leave the site as some sort of surface flow runoff. Once this catchment is developed, though, that ratio sort of flips. And because there's less vegetation on site, you have less evapotranspiration. because you have more impervious surfaces on site, you have less groundwater recharge. And so what you end up seeing is this big increase in surface flow. This is when we're talking about runoff reduction. This is what we're talking about, right? Where we want to reduce this surface flow runoff, because this is what causes most of the downstream issues that we're trying to control. Surface flow runoff is what mobilizes pollutants. Surface flow runoff produces the velocities that cause erosion. Surface flow runoff causes the volumes that overwhelm our sewers and cause CSO spills. So surface flow runoff, this is what we're trying to reduce. So this brings up sort of the first of 4 polls I'm going to have during this presentation. We're going to do 2 right now, and I'm going to launch this. Let's see. So this first poll is infiltration the preferred method of runoff reduction, of runoff control where you work? And I'll just give a minute or so for people to weigh in. Okay, but most of you have voted. I'm going to close this poll, share the results. So it looks like about a 60-30 split here of people who are using infiltration as the preferred method of stormwater control, and about 30% say no. So that's a good mix for this webinar. And I have another poll to take then. Let's see, moving on to poll 2. Have you included bioretention or other infiltration systems into your stormwater management designs? Again, I'll give about a minute here. Okay. So let's share the results of that poll. Most all of you have used bioretention or some other infiltration system in your designs. That's good. I suppose that means you're in the right place. You know, this is a real funny time of transition for stormwater designers. You've got these BMP manuals at the top, all starting all the way at the EPA level, mandating infiltration as the first option for stormwater treatment. And that goes down from the EPA to the states to the counties. But then once you get to sort of the ground level of the site, you have to square those mandates against all the conditions. And some of those site conditions are going to be physical, like slopes and impervious, the infiltration rate of soils, and things like that, things that come with the actual landscape. And then some of it is going to be a little bit more human. You've got contractors and owners who have their own motivations around the development of their site that maybe don't square with the ideals of infiltration. You also have local ordinances that might be slightly contradictory to what needs to be done for infiltration, and I'll get into that a little bit. Some of that is going to be around parking ordinances and things like that, and some of it is just about hydrology, pollutant control, TMDLs, what you can and can't do with your runoff as it leaves the site. So it's a very complicated design problem. If you want to get into the real sort of physical nitty-gritty of volume reduction in bioretention BMPs and other infiltrating BMPs, this is a great place to start. And if you haven't visited the International Stormwater BMP database looking for that kind of information, it's a really great resource. This is a study they did. It's now a little old, 2012, but I pulled off a couple of findings just to highlight here. They showed, of all the studies they looked at, an average volume reduction of 66%, ranging from 56 to around 90% volume reduction based on from bioretention BMPs. One of their conclusions, though, it made me laugh. This is relationships may exist between volume reduction performance and site attributes such as soil infiltration rate below the BMP location, infiltration into native soils. So well, of course, if you have good soils that with high infiltration rates, then runoff reduction is fairly simple. You just put it in the ground and it percolates in, and that's it. But who has good soils anyway? Here's a picture of somebody with their infiltrometer trying to find the good soils on their site. Everybody you talk to has difficult soils and is looking for ways to make better use of the land they have. And then beyond, even if you do have good soils, are you even allowed to infiltrate? There are definitely spots that we've come in contact with where there are protections around groundwater or protections around aquifers. And even though you may have good soils, you're not allowed to infiltrate in certain spots or in certain rates. So one more poll here, just to set the stage. This is, what is your biggest infiltration challenge? And I'll describe these a little bit. Crowded sites, just having the space to put your infiltration. Limited dropper head hydraulically. Can you fit the hydraulics into the vertical space on your site? Failed plantings. Many of these systems have plants established on them. Are those plants staying healthy? Erosion of media. Is the erosion leaving the site? Or something else, something that we haven't identified here. Then give just another couple of seconds. Okay. So about half of you said that your biggest challenge is crowded sites. Almost 30% of you have some other challenges that aren't addressed here. So that's really interesting. And you know, at the end of this webinar, you'll have the option of taking part in a broader survey. It would be great for you to be able to contribute as part of that response, what some of the other challenges are. Be a really useful and interesting thing for us to hear from you. Okay, just make sure I have this right. So I'm going to start off by talking about some challenges around hydrology, and this really ends up being about challenges that have to do with use of space on a site. I don't need to tell you that sites are crowded. You appear to know that. And I don't need to tell you that land is valuable. So some of my citations here are starting to get a little bit old, but the story stays the same. In a rural kind of setting, you might be talking about land values of $50,000 an acre. In an urban setting, you're talking about land values that are much, much higher than that, maybe $1 million or more. And so this is the value of these sites provides a certain level of conflict between people who are trying to infiltrate and people who are trying to develop, because it's hard to do both on the same site. To give an example of this, just to draw attention to one thing, parking space ordinances. The parking spaces in a site are valuable, and they're worth more than just the land that the parking space contains. Because of parking space ordinances like what I'm showing here, you are required to have maybe 5 parking spaces per 1,000 square feet of retail space. So the amount of parking you have on site is directly related to how much retail space you have on site. And retail space is very valuable. So all of these ordinances make it so that there's some real conflict between how much of your parking lot is allowed to be used for planted infiltrating areas. Taking parking spaces actually translates to taking retail space, which is, for a developer, a real conflict. Just if you run the numbers based on some basic estimates of how much retail space costs, the value of a parking lot of a parking space, excuse me, can be somewhere around $5,000 or $10,000 once you take into account the actual value of the entire lot and the way that it gets translated into retail space. Now, I'm going to give a few different tools and tricks that people have used to get the most out of their parking spaces and still meet their infiltration goals. And I'll start off with some ideas that are very kind of straightforward and easy, and I'll get into some that are a little more complicated, could probably have a webinar of their own, but I'll do my best to kind of summarize things. This is an image I lifted from the Virginia Water Resources Research Center, but it shows a diagram, probably the kind of thing you've seen before. We have a bioretention cell, you have sheet flow coming off, but you also have some concentrated flow entering this. And to make sure that you keep those gross sediment and trash under control and get those velocities down, you might need to use a forebay of some kind. And the rule of thumb is often have a forebay that's like 20 to 25% of the volume or footprint of the bioretention cell you're working with. So one thing that people do, and this is another image that I pulled, this is from the University of Washington, Tacoma, is put that pre-treatment, rather than include it as part of the planted area, put that pre-treatment under the parking lot. So you gain some parking spaces based on that. Now you only need space for your planted infiltrating area. Only that has to be subtracted from the parking essentially, and you can put a car on top of your pre-treatment here. So this is a very sort of straightforward thing to do, and is already in use in a lot of places. Pre-treating with a manufactured treatment device has some follow-up benefits. Not only does it keep your trash and floating material and gross coarse sediment under control, but it also helps maintain a tidy appearance rather than having that concentration of trash end up in a planted area that's intended to be attractive. Now it's kept undercover, centralized, and out of sight. These systems are usually designed to retain that material during a large storm, so there's no sense that it's going to remobilize or blow away. Maintenance is a lot easier. You can pull up right over this with a Vector truck, draw out the trash and coarse sediment, rather than go through with rakes and by hand picking trash out of a planted area. And as I was saying, it immediately gives you a 20 to 25% smaller footprint. You've probably run into manufactured treatment devices before. They're very common. Hydro International makes them. We have two products. One is called the First Defense, another is called the Downstream Defender, but there are lots and lots on the market to choose from. So this is right off the bat a very simple way to make that planted area you have a little more efficient. The bigger question though, and the harder one to answer, is what do you do with all the water? So you've got, when you're designing an infiltration system, you have a lot that you're juggling here. You'll have a water quality volume that you're mandated to control, infiltrate. Maybe your site has some low infiltration rates. So what do you do with all that water? Now, it can't get into the ground fast enough, so you have to pond it. But where is your ponding going to occur? And then once you have this water ponded, how fast is it going to, how long is it going to stay there? There may be regulations about how long you can have ponding on a site. And as you're moving this water all around your site, trying to get creative about where it goes and how you're infiltrating it, you may have requirements about minimum orifice sizes, and at the low flow rates that we're talking about here, that can be a challenge. So all of these things are hard to juggle. And just to put some real numbers to this, it's not uncommon to have to manage a 50-year storm. Infiltration rates on site of less than 1 inch per hour. Maybe hydraulically you only have less than 12 inches of vertical space for ponding. It's very common because of vector control that cities will ask that water not be kept on site for longer than 24 hours. And lots of areas say you have to have orifices big enough to pass a soda can. So that's, means you need to have something around 3 or 4 inches. So all of these things play together to make for a really challenging design problem. One way that people deal with this is to essentially decouple their water storage from their water infiltration. And if possible, arrange it so that they're storing their water upstream of their infiltration system, underground where you can park on top of it, essentially. And so here's an example here with some attenuation upstream of a bioretention system. So this is storage under parking. You've probably run into these sorts of storage tools before. There's lots of ones on the market. These arch storage chambers you've probably seen before. These are concrete chambers, these sorts of open structure plastic blocks that people use for storing water. What I'm going to talk about are these guys down here. And these are a little rare. Maybe you haven't seen these before. These are called vortex flow controls. Hydro makes the ones that are on the left here. The trade name that we use is Hydro Brakes. But they're made by other companies as well. These are ones made by other people. They're very, very common in Europe, often installed by default. A little less common in the US, but starting to catch on in some areas. And a vortex flow control is a sort of a constant discharge valve in a way. And if you're somebody who deals with orifice flow controls regularly, you'll recognize this sort of head discharge curve, where if you have an orifice and your flow starts to increase, your head starts to increase as well, usually based on the square of the velocity. So you end up with this sort of curve here. With a vortex flow control, you have this sort of strange looking head discharge curve that's sort of S-shaped. And what happens is as the flow increases, head increases, just like in an orifice. But at a certain point, water begins to swirl around in this vortex valve. And now it begins acting like a constant discharge valve, where flow does not increase anymore. It stops increasing, and now just head increases all the way up to a certain design point that can be specified. So this has a whole bunch of uses, and I'm going to kind of give a couple of illustrations based on a project that we were exposed to. This is a site, you might have had similar situations yourself. There's 400 plastic arch chambers here, upstream of some infiltration. There's 9 infiltration basins offline. Now these infiltration units, they could be a lot of different things. They could be injection wells. They could be a large sand infiltration unit. They could be a variety of different things. But for the sake of conversation, we're just calling it 9 infiltration basins. So I'm going to start getting into some numbers here. What the vortex valves allow you to do is really optimize the use of the storage media that you already have on site. So for example, in this case, you had these 400 units of plastic arch chamber, and they were upstream of a diversion structure. And the engineer who designed this said, I'm going to use a 4-inch orifice. Well, why did they decide that they were going to use a 4-inch orifice? I don't know. Maybe it was local regulations. Maybe they had had a bad experience with small orifices in the past and felt that they needed to use a 4-inch orifice. By using a 4-inch orifice here, they ran this through their HydroCAD or whatever hydraulic modeling software they were using, and ended up with a flow rate of 0.5 CFS coming from the storm attenuation. And they looked at the infiltration rate that they were working with and said, okay, 0.5 CFS, I'm going to need 9 of these infiltration units. It's going to take around 2,000 square feet of space. I'm going to need to make room for those things there. And I'll end up storing around 13,000 cubic feet of water in my upstream storage. But if you notice, that upstream storage, even though the whole unit is installed, it's only being half used. And this is due to the nature of the storm hydrograph. But you're really not making full use of that upstream storage. Now, if you swap out that 4-inch orifice with a 4-inch vortex valve, a couple of things happen. One is right away, your flow rate drops down. This is the maximum flow rate leaving. Your maximum flow rate drops down to under 0.2 CFS. So we were at 0.5 CFS. Now we're down below 0.2 CFS. So you can get away with a much smaller infiltration area. Now, maybe they only need less than 400 square feet there. In addition, all of that water is being stored in plastic media that's already installed. So what's happened is it's gone from being 50% used Now, okay, so we're storing 17,500 cubic feet here in this plastic arch chamber. We're using it more efficiently. We're using 70% of it now. So that's great. But how does this happen? It all comes down to this kind of strange hydraulic curve that vortex flow controls have. As the flow rate increases, it is letting out flow and not using the storage at all until it gets to just this design point of 0.18 CFS. And then at that point, it stops acting like a 4-inch orifice and it starts acting like a 2-inch orifice. Physically, it doesn't change. It's only hydraulically acting like a 2-inch orifice. So that soda can still pass through, but the flow rate reduces. So you might be saying now, well, you know, that doesn't really apply to me. I'm fine using a 2-inch orifice. There's no regulations around that in my area. And I'm very comfortable putting an orifice inside a screen and protecting the orifice that way. And so I'll just use a 2-inch orifice. There's one other way that vortex flow controls can save you some space on site. It's a little more complicated and it could be its own presentation, but I'm going to give it a go. The 4-inch vortex flow control has this strange shaped curve where it starts off acting like a 4-inch orifice, and then it kind of transitions and it begins acting like a 2-inch orifice. And so if you had this red curve that is the way a regular 2-inch orifice would work all the time, there's a space in between, and that space kind of represents the volume that you can save that you don't even need to store if you design your site appropriately. So here's an example, and for those of you who use HydroCAD regularly, these graphs will look very familiar. For those of you who don't, they might look very strange, but this is a comparison between a 2-inch orifice and a 4-inch vortex valve. Same site as we were talking about before. And just to highlight a couple of things, we're running a hydrograph through here that's a sort of a peaky type 1A storm, high intensity peak to it. And both the 2-inch orifice and the 4-inch vortex valve have around pretty close to the same maximum discharge flow rate, just about 0.17, 0.18 CFS. So the maximums are the same. But if you look at the storage required, the 2-inch orifice requires 0.07 acre feet of storage, and the 4-inch vortex valve requires 0.05 acre feet of storage. So this is a 33% savings. That's literally, you don't need to use a third of the plastic arch chambers that were shown on the original design. This seems a little strange. It gets stranger. If you had a storm that is even less intense, has a less intense peak, this is a Florida DOT storm. I think some of the storms in the Pacific Northwest are good for this as well. And you compare the hydrograph of a 2-inch orifice to a 4-inch vortex valve. Again, maximum flow rate leaving this is again the green is your influent hydrograph, the blue is the effluent hydrograph. Maximum discharge is about 0.17, 0.18, about the same. The 2-inch orifice needs to store 0.06 acre feet. The 4-inch vortex valve needs to store 0.03 acre feet. So that's a 50% savings. Literally, you can use half the storage media, half the arch chambers. So how does this really happen? What's going on here? Just to explain it, the green line, that's your influent hydrograph. The blue line, that's your outflow hydrograph. So the space in between, anytime you have inflow that is greater than your outflow, that's volume that you have to store. And this is cubic feet per second, and this is time down here. This is volume we're representing up here. You have to store all this volume in the red, because the 2-inch orifice starts storing right away. The 4-inch vortex valve doesn't start storing until the storm gets to the design point of 0.17, 0.18 CFS. At that point, now the 4-inch vortex valve starts acting like a 2-inch vortex valve. That's when it starts storing. So it only has to store the peak of the storm rather than the whole upper leg of the storm. That's how it happens. It's a little complicated. If you have questions, send them to me. Send them as part of the final survey, and we'd love to talk to you about it. So just a summary about saving space on site. Quick way to reduce footprint is put your pre-treatment under a parking space. You can use an MTD to do that, manufactured treatment device. Immediately, you can save 20 to 25% of the footprint of that infiltrating system. You can use a vortex flow control, particularly if you have orifices that you're using around 2 to 4 inches. That's a great kind of rule of thumb of where the vortex flow controls operate their best, and they allow you to use the full use of whatever storage chambers you have on site. And they may be able to reduce your storage volume as well, depending on your storm, from 10 to 50%. So now I'm going to go on and talk a little bit about media challenges. This is what you've handled where your water is going to go. Now, what about this actual infiltration system you have? Again, this figure that I have here may have changed. You know, I think I dug this up. It was almost 10 years ago now, and green infrastructure's come a long way since then. And whether you call it green infrastructure or LID, you know what I'm talking about. But the fact still remains, in order for a bioretention system to perform well, there are lots of factors at play. And most of them are out of the control of the designer. While they might have some control over prevention of erosion in the design and a little bit of control around pre-treatment, some of that comes down to good site conditions. Some of it comes down to, was the design built right? Whether the system stays working well comes down to good maintenance, and is the owner going to stay involved? And the installation of media can be a sensitive thing. Protection during construction, making sure that the contractor who's putting it in knows what they're doing is not something that the designer always has control over. So even if we're seeing success rates of 2 and 3, that's a 30% chance that something's going to go wrong, and that's, you know, reason to have your eyes open. Failed plantings, while maybe not that expensive, is still a matter of managing your reputation, and nobody wants to get a phone call that says, hey, those plants that just went in, they're all dying. What's going on? So, you know, this is something that people need to understand. And the temptation to fertilize all the plantings, and then you end up leaching nutrients out. So it's complicated. Managing high flow rates. How do you manage heavy sediment and trash, erosion of sediment, of media, all of this sort of thing? It can lead to performance degradation. How is that designed? So what happens? Oh, we're going to do a poll. Here it is. This is the last poll. What is most important to you when you're designing infiltration? Give it another 10 seconds. So it's kind of a split here. Runoff reduction performance, regulatory approval. You know, and in a lot of ways, those go hand in hand, don't they? So that's really useful information, and we've heard that from a lot of people. You know, one way that people will mitigate the risk of designing their own infiltration system or bioretention system is to buy a manufactured infiltration system or buy something off the shelf. And when you do that, you also buy with it a guarantee of performance, and that's often a useful way to take some of that risk off of your own plate. So Hydro has their own off-the-shelf engineered infiltration system. There are quite a few of these on the market. This one is ours, and what we've done is we've really tried to maximize some of the features that people have told us are the most useful features for bioinfiltration and runoff reduction. So just quickly, sort of the parts of this, we've got a really open structure. The point with the bioinfiltrator was that people said we need to have the most contact with the native soils to make sure we have as much infiltration as can be possible. We don't want to be limited by the concrete box that is provided. And so these components make up an open system that allow for runoff to go right into the native soils and allow tree roots to migrate out and keep that soil free flowing. This is what it looks like when it's installed. No concrete box, maximum contact with the soil. The roots can keep that soil open, avoiding the plant failure. You can kind of see it going in the ground here. And because there's no concrete box, it's lightweight, it's modular, it's easy to install. There's no crane needed for installation. You can pick it up by a landscaping crew. Everything is made of stainless, aluminum, rubber parts that can be easily handled by a couple of people. Maintenance is simple. I think you could see at the top here, there's sort of these pavers on the top. These pavers are recycled rubber. And so when these pavers come off, now you can see there's a concentration. All of the trash and leaves and material that would otherwise clog a filter have been collected in this spot. You pop off the paver and you can pull these out by hand. It's very simple. And, you know, I had mentioned managing velocities. Erosion of media is a big concern. In some manufactured units, it's managed by sort of some rocks or riprap being installed in the throat of the unit. We opted for a more engineered solution. We have a baffle here that intercepts the flow as it comes in, slows it down, allows it to deposit the coarse sediment, allows trash to deposit here. This is sort of this outer pre-treatment zone that concentrates all of those heavy pollutants. But the tiles are shown off here. Normally, that would be kept out of sight, so everything stays tidy looking. The inner infiltration zone, that stays open. And so this is the planted area. Plants don't have to compete with all this coarse sediment and trash. That stays protected and open for maximum infiltration. The design is meant to be flexible and modular for folks who are designing streetscapes. So the base model is this 4x6 design, but they can be nested, turned, or arranged in different patterns to come up with sort of different designs that might fit the space that they're being used in. Or use them all the way down to median. This is sort of, you know, one use that we imagined here. And finally, if the idea of managing plants isn't in the cards for the particular space where they're being deployed, they can be provided with streetscape features. So perhaps a kiosk or a bike rack or a bench. So, you know, this would be a way that they could fit into an urban environment, maybe without the concerns that come along with plant maintenance. So a few conclusions here. Every site is different, and runoff reduction is complicated. And for engineers who are designing the runoff reduction for sites, they need a broad toolkit that can meet lots of different conditions. Some careful application of engineered devices can help green infrastructure go a long way. So manufactured treatment devices as pre-treatment, storage and vortex valves with flow control can help put your attenuated flow and help store your flow under parking. Manufactured bioretention or infiltration can give you that guaranteed performance that takes the risk off of your plate. And Hydro International has these products. They can help you meet your green infrastructure challenges, and we're happy to talk to you about how we can help. So that's the end of the webinar. There's going to be a survey coming your way. If you take this survey, you'll be entered to win a $50 gift card at Amazon. Winners will be notified this week. PDH certificates are available for this presentation. They'll be emailed out no later than tomorrow. So keep an eye on your inbox, and those will be coming your way from Hydro. And that's it. Thank you very much. This is my contact information again. Feel free to contact me directly, and I really appreciate you sitting through the webinar. Thanks again.